Hello, everybody. Welcome back. Today we're going to do section 5.2. And in this section, we're going to talk about properties of logarithmic functions. In section 5.1, you learned basic exponential functions like y equal e to the x, for example. And any good exponential function or any good function in general has a workable inverse function that undoes its actions. Logarithmic functions are the inverse functions to exponential functions. So the opposite of doing an exponential is doing a logarithm. And eventually, in a couple of sections, we would like to start doing derivatives of exponential functions and logarithmic functions. But before we get there, we need to review some properties of both so that we know how to do algebra with the logarithms and exponentials before we start doing derivatives. In this section, we're going to think about the relationship between exponential functions and logarithms and some properties of logarithms themselves. This will be helpful once we do eventually start doing derivatives again. So you might think of section 5.2 as more of a college algebra review. Now, a logarithm is always written in this style, y equal log base b of x. So this b here is called the base, and this is a y value. Now, you can think about exponential functions, a number raised to a variable power, as being a logarithm written in a different language and vice versa. You can convert an exponential equation into a logarithm. Just like if you're translating a sentence from English into Spanish, you have certain sentence in one language that then gets translated into a sentence in a different language. So you can think about logarithms and exponentials to be relatively related this way. Let's take a quick example of an exponential function or expression that makes sense. So we know that 2 cubed is equal to 8, right? 2 to the power 3 is 8. So if we compare this sentence, 2 to the 3 equals 8, to this formula, b to the y equals x, in my b spot is the number 2, in the y position is the number 3, and in the x position is 8. You can rearrange this sentence into a log, into y equals log base b of x. Our y is 3, y equals log base, what was our b? Our b is 2 of x. So we just translated an expression that makes sense to us, 2 cubed is equal to 8, into a logarithmic statement. This is the same statement, just written as a logarithm. Now, it is more advantageous of us to think of the sentence this way, 2 cubed equals 8. But sometimes logarithms do come in handy when I'm solving for things or dealing with other types of functions. So it is good to know the properties of logarithms and how those can translate back into exponentials and how to deal with those separately. So let's talk about what logarithms look like. If I have a logarithmic function, y equals log base b of x, it has a graph, as these types of functions always do. And when you graph it, it looks something like this. So if, as provided that you have a log base that has not been shifted, it'll have some varied steepness of this shape. It'll start off down low and go up slowly to the right, but it's going upwards just at a very slow pace. This is what a logarithm looks like if it hasn't been shifted or rotated or flipped or anything. So if you notice, this graph doesn't actually extend over here into these two quadrants. So that is to say, my x is never on the negative part. I never have any negative x's on my graph. So that means, as we see, the domain of a logarithm is 0 to infinity. That is, I'm only using positive x values in my graph. So if you ever tried to plug in a negative number into a log, you would get an error in your calculator because your graph doesn't even exist for negative values of x. So we could never plug negative values of x into a log function. The range, the set of y values that your graph takes up, is all real numbers. So while the x values your graph takes up are all the positive x values, all the y values are all of them up and down. The graph goes all the way down and all the way up. So the range is minus infinity to infinity. So mostly what we're going to need to remember is that the domain of logs are positive x values. That is, I can't plug a negative number into a log. There is one particular logarithm that is particularly interesting to us. If you have, for my log base b, if that b for your base is the number e, then log base e is a special log that they call the natural log. The natural log is written as ln of x. And whenever you see ln of x, that means it's understood log base e. The base is e. So we often, in this section and in this course, use the natural log whenever we're doing derivatives. And most of our formulas will involve the natural log. But remember, natural log is a regular old logarithm with base e. We will need to use some of these properties today, but before I keep rambling on and talking about the log properties, let's go use our last page conversion, and we'll come back and discuss these when we get to them. So let's come down here to our practice problems. It says convert the exponentials to logarithms and the logarithms to exponentials. So we want to come back here and use this translation statement, and they want us to basically translate from one statement to the other, from one language, so to speak, to the other, back and forth. So if you have one in one language, translate it to the other. So I'm going to write our conversion right here. If I have b to the y equals x, then this converts to y equals log base b of x, and vice versa. If you have y equals log, it converts back into b to the y equals x. So the statement that I'm looking at is my b to the y equals x statement. It's an exponential. It's got something with a power on it. And they want me to convert this into a logarithm. So for that, we have to compare, figure out what all my letters are. Based on this formula, what's in my b position? Looks like 2. Hey, it looks like we already did this one. In my b position is 2, and my y position is 3, and then my x position is 8. So if you rearrange this into y equals log base b of x, you have y, which is 3, equals log base b of x, or 8. No, it looks like I did that mistake over here too. We translate 2 cubed equals 8. You have 3 equals log base 2 of not x, 8. So I did the same example back here, but I gotta fix that. It's log base 2 of 8. All right, here we are. 3 equals log base 2 of 8. This is a statement that makes a little more sense. 2 cubed is 8. That's something you can verify and punch out. We know that's true. But then we just translated it into a logarithm. So this is the logarithmic equivalent of that statement. It's just written in a different way, a different language, if you will. But that's what it looks like. Let's do this again, making sure to keep our formula handy so we don't have any mistakes. B to the y equals x converts into y equals log base b of x. So this is my next statement. 3 to the 4th power is 81. This is verifiable, right? If you punch in your calculator 3 to the 4th, you get 81. But they want me to translate this into an a logarithm. This is an exponential form. It's something raised to a power. So we want to write it in its logarithmic equivalent. So if you like, write down what each of these things are. What's in my B position? In my B position is 3. What's in my Y position? In my Y position is 4. And what's in my X position? My X position is 81. So if I'm going to rearrange this into this statement, I've got to rearrange it as y equals log base b of x. Y equals log base b of x. And there we go. We've translated it. Y equals log base b of x. We took an exponential and we wrote it as its logarithmic equivalent. Now let's do this. Keep doing it. Keep practicing. This time, I have another exponential. 2 to the x equals 32. So, this one's got a variable in it. But it's still an exponential form. It's still a number raised to a power or equals some other thing. This would be something that we could potentially solve for x on, but that's not what they're wanting me to do. They're not trying to make me solve for what x is. They just want me to translate this statement into its equivalent statement as a logarithm. So if we translate b to the y equals x goes into y equals log base b of x, what is in all of my positions? So what's my base b? My base b is 2. What's in the power position? Looks like in my power position is x. And what's on the right-hand side? It's 32. So they did kind of mess with their heads a little bit when they used x here in the power, and I have x in my formula. But we're looking at this side. What is this b? This b is 2. What is this y? This y is x. What is this x? That's 32. So when we want to rearrange this into y equals log base b of x, we have y is x, equals log base b, my b is 2, of x, and what is my x? My x is 32. We have x equal log base 2 of 32. So we translated this statement into its logarithmic equivalent using that formula. So this is my answer. This was the formula that I used from up there, but I'm going to scratch it off so we don't get it confused with what I've got there. So here it is. When they start throwing variables in this, I find it helpful to, when I have an exponential, 2 to a power equals that, you always kind of start with the power and go, okay, the power x equals log base 2 of 32. So power equals log of the bottom of that. Kind of goes around in a circle. So x equals log base 2 of 32. For this one, it'd be power 4 equals log base 3 of 81. Kind of goes around in a circle there. Okay, so then here's my statement. Log base 2 of 16 is 4. And they said that I'm supposed to be translating statements. This time, they gave me a logarithm. In my previous example, they gave me an exponential and told me to convert to a log. Now they're like, okay, here's my log, convert it back into an exponential. So now we're going to go the other direction. They're giving me a logarithm and they're going, okay, now write it as a power function. Now for this, we come back to our formula. We're looking over here and we want to compare with this formula. What's in my y position? What's in my b position? What's in my x position? So for this, it might be helpful to make a running list. If I'm comparing this log statement to this log statement, this to this, it might be helpful to write it in the proper order first. I had y equals log. This is log equals y. So let's flip this statement to where it kind of lines up with my formula. 4 equals, let's put the log on the right-hand side. There we go. 4 equals log base 2 of 16. So let's compare that log with my formula log. What is in my y position? In my y position is 4. What is in my b position? My b position is 2. And what is in my x position? My x position is 16. So we make a run-in list over here, and we have to convert this to y equals log, or converting from a log into an exponential. So converting from a log to over here. Now that we know what y, b, and x are, convert back to this statement. B to the y equals x. So here's my b, there's my y, there's my x. Write it all out. B to the y equals x. So I rewrote my log as its exponential equivalent. Just rewriting it in a different language. 2 to the 4 is 16. All right, let's do that again. I got my log, and they want me to convert it to an exponential. So I want to write it as a power thing. And if I compare, again, let me rewrite my conversion down here so I don't have to keep moving my paper around. We had b to the y equal x, converts to y equals log base b of x. And so I'm starting on this side. I want to convert my log back to my exponential. So let's compare this log with that log. It's a little bit backwards. They have, in our version, in the formula, the log is on the right-hand side. This time it's on the left-hand side. So let's just rewrite my statement as 3 equals log base 5 of 125. We're just flipping it so that it matches my formula style over here. So I'm on this side. Let's label what is my y, what is my b, what is my x. So you might make a running list over here. It's like, okay, if I compare this log to that log, what is in my y position? In my y position is the number 3. What is in my b position? My b position is 5. And what is in my x position? My x is 125. So when I convert this to this side, remember I'm trying to go from this to that, I need to rearrange everything into b to the y equal x. B to the y equals x. So the statement that we make is 5 cubed is equal to x, or x is equal to 5 cubed. That's my statement. Another nifty shortcut that I find visually for how to convert this without like making the whole list thing. So this is very proper. This is write out y, what's b, what's x, convert it. But if you want to try to do it without looking too much, you always want to start on the base in your logs and go, okay, 5 to the power of 3 equals 125. So you start at the base on the log, put it to the power of the other side. So 5 to the power of 3 is equal to 125. And so same up here, you'd start at the base of the log. 2 to the power of 4 equals 16. 2 to the power of 4 equals 16. So if I apply that round logic here, you start at the base. E to the power of 2.079 equals x. E to the 2.09 equals x. And so that's my statement. E to the 2.09 power is x. I'm not supposed to do anything with it. I'm just supposed to convert this sentence into that sentence, and we go, okay, that's it. We just converted the sentence. We're done. That's how you can convert exponentials to logs and logs to exponentials. That little conversion there. That comes in handy when you're solving exponential functions. If you want to solve for x in a log or solve for x in an exponential, you need the inverse function. So if you've got an exponential function, you need a log because the log is the inverse. You need one with, you can't have one without the other if you're going to do algebra. So knowing the properties and how to convert from one to the other is really handy. Number 2 says use the properties of logarithms to expand the logarithmic expression. So to do this problem, I need to go back to that list of stuff I said we'd come back to when we got to it. Well, now we've gotten to it. Here we go. Logarithms. Logarithms are quirky little things. They have their own set of rules that only apply to them on how you can simplify them. It's very interesting. So here we go. Here's some properties of logs. The big ones that we're going to use a lot are mostly the top three. Logarithms are interesting. If you have a log base anything, and inside that log, you have something that is a product, a multiplication. If you have something that's a multiplication, it actually expands. Now, it doesn't expand in the way that kind of algebraically makes sense to us. You might think that this kind of, in a way, distributes in to where it might make it log of m times log of n because there's a product in the middle. It actually doesn't work like that. If you're going to expand something that's multiplied, it's not that you're distributing in the log. That's not what happens at all. What happens is this log splits into two. So if you have log base b of that product, m times n, and that can be like anything, 6 times 5 or x times y, then this log splits. It splits into two different logs, log base b of the first thing multiplied plus log base b of the second thing multiplied. Like these, there's not a multiplication in here still. I had a multiplication inside, and this sucker is split up into two different logs with a plus sign in the middle. Nothing here is multiplied. This is like breaking the laws of physics. We have a multiplication inside the log, and that log split up and turned into an addition of those separate logs. That is a very interesting property, and it's unique to logarithms. You cannot pull this off in any other type of function. Similarly, if you have a log base b of anything, and you have m divided by n, so I have a division happening here, one divided by the other. This does not work that it becomes log of the top divided by log of the bottom. Oh no, that's not true at all. If you have log base b of m divided by n, this log splits just like the one up here did. It splits into two different logs, whereas log base b of the numerator minus log base b of the denominator. I have a division, a divide, that turns into a subtraction of two separate logs. So a log of one thing divided becomes two separate logs subtracted. Again, this is a property or a type of trick that's unique to logarithms that you can't do any other time. Now, so divisions of inside one log turn into a subtraction of two different logs. It is not correct, so don't even write what I'm writing here. It is not correct to say this becomes log of m divided by log of n. That's not how the property works, unfortunately, even though that is algebraically consistent with what we are generally used to. So we practice these properties today because they're a little bit weird and they take some getting used to. That's why we bothered to review these before carrying on. Our next property, which is again very different and unique to logarithms, is that whenever you have a power on something inside your log, that power can be brought down and treated as a constant. So for example, if I have log base b of, say, x squared, where that square is on that x, by this property, this is equal to, it's the same as saying, where I brought the 2 down, 2 times log base b of x. So this is the same thing. In no other universe can you bring down a power on something and say that it's the same as being multiplied. Well, in logarithmic world, you can. This is accurate. You just have to make sure that this power is on the whole argument inside the log. So we're going to practice using these properties because they take some getting used to, and we have a lot of do's and don'ts on these. Now, one of the don'ts is that I can't take a log, so in this case I got the natural log, of something added, and I can't split it. So what you cannot say is that this is ln of x plus ln of 5. If you have an addition or subtraction inside your log, you cannot split the log. That is immobile, inseparable, locked in forever. There's no splitting this into two different logs. if you have an addition or subtraction, there is nothing I can do to simplify that. That is how it is, and nothing's going to work. You can't split this as log x plus log 5. Doesn't work that way. So don't do that. That's bad. Similarly, if I have, and I'd mentioned this earlier, ln of, say, x divided by y. You cannot write this as ln of the top divided by ln of the bottom. Again, that algebraically makes sense, but it doesn't work that way with logs. You have to use the subtraction property up here to split that. Similarly, if I have log m divided by log n, this does not become one log of log m over n. There's no way I can simplify that. So we have a lot of do's and don'ts with logs, and it takes some getting used to. So we're going to come back here and practice. So now that I scribbled on the front page, let's do a couple of real quick examples in the top margin of how to use a couple of the top ones, top properties. We had said that log base b of something multiplied, m times n, becomes log base b of m plus log base b of n. So it splits into two logs, and those two separate logs are added. So as an example of this in motion, let's say that I have log base b of 2 times 3, which is 6, right? 2 times 3 is 6. But let's say I split this up into two things multiplied. Applying this property means that this is the same as having log base 2 of the first thing multiplied, the 2, plus another log with the same base of 3, the other thing multiplied. Log base b of 2, so make that a 2. Log base 2 of 2 times 3 equals log base 2 of 2 plus log base 2 of 3. You can split this up into two logs that are added. So this 2 kind of manifested because I copied it down. I meant this to be 2. Log base 2 of 2 times 3 is log base 2 of 2 plus log base 2 of 3. And similarly, what if I had log base 5 of whatever, x times y? This becomes log base 5 of the first thing multiplied, x, plus log base 5 of the second thing multiplied, y. This is a neat little property, and again, it's unique to logs. If I use the division property real quick, let's say I have log base 3, or base b of 2 divided by 3. Then our other log property of division said that division split into subtractions. This becomes log base b of 2 minus log base b of 3. So log of the top minus log of the bottom. This is how they split. So let's apply these. You can use these formulas both ways. You can take one log and split it into more than one log. That's called expanding it. Or you can take more than one log and scrunch it down into, go in this direction. Take two logs that are added and scrunch it down into one that's multiplied. So it depends on what you want, which way you want to go. So some of our directions will say, start with one log and expand it into more than one. Or they'll give us more than one log and tell us to scrunch it back down into one. So let's practice going both directions. It says use the properties of logarithms to expand these expressions as much as possible into sum or difference of logarithmic expressions. So when they say expand, that means we're going this direction. I'm going to start off with one log and I'm going to keep splitting it and doing stuff, and I'll have a whole bunch of them at the end. So like in problem A here, I have ln, so this is a natural log, log base e, of all of this. So all of this is inside the log. And this is where we kind of have to, what they want me to do is use these properties such that we start off with one log and use the property that makes it turn into more than one, expand it. So we have to figure out which properties are applicable to this. Well, first off, I'm going to rewrite my root as a power. I say this all the time in calculus, but roots shouldn't exist. We always have to rewrite them anyway. So as soon as we see square root of z, We should write that as z to the 1/2 power, right? Because it is a power. Now, when I look at this, I notice that this is ln of a fraction. Like, I have some x's and y's and z here, and there's stuff multiplied in the top, but the overall form mostly is I have a top divided by a bottom. So I'm going to use this top divided by bottom, this division property, to split my log up into two logs that are subtracted. So the log property went that log of a fraction became log of the top part, which in this case is x squared y to the 5th, minus log of the bottom part, which is z to the 1/2. So now I've used a log property, and I split my log into two different logs. But we're actually not quite done. I'm looking for every instance that I see something that is divided, it becomes a subtraction, and any instance that I see something multiplied, that becomes an addition. So I'm looking for, do I have a couple of things that are multiplied in one of these logs that I can split up? And to that, we say, yes, I actually have ln of x squared times y to the 5th. And then we go, oh, I have two things multiplied in there. So that means, according to this property, this log should split into two different logs that are added. This should be ln of the first thing multiplied, x squared, plus ln of the second thing multiplied, y to the 5th. And then this log from before gets copied down. So we get here, and we've applied the log properties, and then we have to ask ourselves again, I was like, okay, do I have any multiplications in here? Do I have any divisions in here? I'm looking inside the logs. Any multiplication or division there? Nah, the powers don't really count for multiplication and division. We'll take care of the powers in a minute. That's not multiplied by anything else or divided by anything else, and neither is that. Z to the 1/2 is not multiplied or divided by anything else. So we're good on the expanding it. But they did tell me, it's kind of the last set of directions, it says no term should contain exponents. So they want me to use that third log property that I showed on the last page, where we said that if you have a power on your argument in the log, you can actually bring those powers down. So we're going to use that property. This power, I can actually write out front. Same with the 5, same with the 1/2. This becomes like I took that 2 and I just plopped it down in the front. 2 ln of x. I stole its power, so it's no longer there, so it's just x to the first power, plus 5 ln of y minus, and that 1/2 comes down, 1/2 ln of z. And there we go. We've expanded my logs, and all of my logs don't have a exponent on the inside of my log. So we're done. We went from one log with powers to 3 separate logs where the powers are now coefficients. We've expanded. So let's do this again. I'm going to expand my log. Now this is one log. This is ln of all of that. So this is one log with a bunch of stuff inside it. And so I have to ask myself again, like, okay, do I have any multiplications or divisions in there? And when I look at this, we go, oh yeah, we have one big division, because this is one big fraction. So since this is a fraction inside, I can use that first log property that said that fractions split into 2, where I have ln of the numerator minus ln of the denominator. So this is going to become ln of all of everything that's in the top minus ln of all of everything in the bottom, which is x minus 7. So that splits up, and at every step I have to ask myself again, it's like, okay, does either one of my logs contain a multiplication or division? And to that, my first one does contain a multiplication. I have x plus 2 times x minus 5. So I'm going to do one more split. We go, okay, since this ln has a multiplication here, this thing splits into 2 logs that are added. You're going to have ln of the first thing multiplied, the x plus 2, plus ln of the second thing multiplied, the x minus 5. And this log from before gets copied down. At every stage, I have to ask myself again, okay, do any one of these three logs contain a multiplication or a division? And the answer there is no. This is an addition, that's a subtraction, that's a subtraction. Those can't split. So remember, I can't write this as ln of x plus ln of 2. That's not how the splits work. Splitting your log only works if you have a multiplication to split into an addition or a division to split into a subtraction. The addition and subtraction, you can't distribute those in. I can't distribute that log to both. It doesn't work that way. So this is as far as my logs will split. It's as far as I can go. And then my last question is, do I have any powers on the outside of these that I can bring down? And no, we do not. There's no powers on the outside of those parentheses to bring down. So there's no coefficients on the outside. We are done here. That's my fully expanded logarithmic expression. So now I go down to here, and they have ln of xy to the fourth divided by ln of x to the fifth. Now, I had mentioned before that, well, actually, let's just highlight here. If I zoom out, what's the difference between this log and the previous two? This log up here was ln of a fraction. So because this was a fraction inside the log, I could split it up into a subtraction. Same goes with this one. All of this was inside that log, so when I had a division, a big fraction, I could split this up into two things that were subtracted. The difference between this one and this one is, this is all inside of one log, but this has two logs, and the logs are in the top and bottom. This isn't a log on the outside. This isn't ln of xy to the fourth over 5. This is ln of that divided by ln of that. So this does not split into a subtraction. Splitting into a subtraction only counts if the thing that's divided is inside one log. This is not that. I have division of logarithms. So whatever I end up doing here, I'm going to have a logarithm in the bottom and a logarithm in the top. This does not split into a subtraction. But I can kind of work on each of these two things separately. If I look at just the bottom, ln of x to the fifth, can I simplify that any? When I see it, I see I have a fifth power on the x, so by that little power property, I could plop that 5 down and make that 5 ln of x down there. Now in my top, I have ln of x times y to the fourth. And I notice, oh, for that little log up there, I do have a multiplication inside of that log that's in the top. So that means my top log can split into two logs. It'll split into ln of, maybe I couldn't crisscross these, ln of the first thing multiplied, x, plus ln of the second thing multiplied, y to the fourth. ln of the first thing multiplied plus ln of the second thing multiplied. I can go one more step because I go, oh, that y has a power on it, power of 4. I can plop that 4 down. So that becomes ln of x plus 4 ln of y, all divided by 5 ln x. Now this doesn't split up anymore, for reasons I'd mentioned before. I can split up this top one and simplify that bottom one kind of separately. But they have to stay divided. And then we're done with this one. So again, this one splits because this is a fraction inside one log. This doesn't split because this is a fraction of logs, not inside one log. All right, let's do one more example here. We have ln of 5x squared minus 45x plus 90, and they say expand your logarithm, right? Make more than one log, split stuff up. But the problem is, as we've already said and established, that you can't split up something that is added or subtracted. It doesn't count. I can only split up things that look like multiplications inside or divisions inside. This is something that's added and subtracted to where we go, okay, hold up. That ain't allowed. So if we can't split it up the way that it currently looks, maybe we can do something to the inside, I don't know, like factor it so that it no longer looks like something added and subtracted. Factoring means you make something that's added and subtracted look like a multiplication. So if we factor inside, then it will look like a multiplication and we can get something with it. So let's just look on the inside of this thing and try to factor this and see what we can make it look like. So that's an ugly looking quadratic. I don't want to try to factor it as it sits, but maybe like, let's try to pull out a 5 first, away from 5x squared minus 45x plus 90. So I have 5 times x squared minus 45 divided by 5 is 9. And 90 divided by 5 is 18. So if I pull out a 5 from there as the greatest common factor inside my log, then I have x squared minus 9x plus 18 there in the middle. So then I'm looking at, okay, let's now try to factor this part. How do I factor x squared minus 9x plus 18? I'm looking for factors of 18 to add up to minus 9. So it might take a second to think about it, but that part can factor into x minus 6 times x minus 3. And remember, this is all inside this log still, this natural log. So I went from this to this. I haven't split anything yet. All I did was factor the inside and make it look a little bit different. So if I can't expand this, can I expand this now? We can, because now I have something that is multiplications inside. That's the ticket. Those can split. So I have 3 terms multiplied, 1, 2, 3. This will turn and split into 3 logs added together. This becomes ln of 5 plus ln of x minus 6 plus ln of x minus 3. Very nice. So we split our logs, and we always have to cautiously ask ourselves, okay, now that we split it, is there anything else that splits? So I have to ask myself, are there any multiplications still? Are there any divisions still? And for these, when I look inside the log, no multiplication or division, no multiplication or division, none there either. So none of these 3 will split. And I don't have any powers on the 5 to bring down. I don't have any powers outside of x minus 6 in parentheses to bring down. So there's no powers to plop down out front. So this is as simplified as it's going to get. All right. So we've just been taking one log and splitting it up into several. Let's do the reverse motion now. So let's say that I have a whole bunch of logs added and subtracted. What if I want to scrunch them and squish them all back down, back into that one log? That's called compressing your log, or writing your log as a single, writing your expression as a single logarithm. So that's number 3. It says, okay, now use properties of logarithms to write these expressions as a single log. So they're going to give you more than one log, and they want you to squish it back down, crunch it back down into one log with no coefficients. So the process that we've been doing before is first split any multiplications or divisions and then bring down your powers. So if we're going to do the reverse motion, you have to do the motion in the reverse order. If I have any numbers out front of my logs, that means they were originally powers, and you'd have to move them back up before starting to scrunch your logs back down. So when I look at this, and I'm looking at a logs that have already been expanded, if there's a number out front, that means that used to be a power. So the first thing you want to do when you're going to compress your logs back down into 1 is take any numbers out front and put them back as a power on the x. They had been taken down. So this is ln of x to the 5th. And since there's no number in front of there, that's plus ln of y. There's my expression. Now, if we're doing this in the reverse motion, additions scrunch back into a multiplication inside my log. So if I have 2 logs of the same base, so this is the natural log, and they're added, that means they can be squished down into 1 log with the arguments multiplied, x to the 5th times y, all inside of 1 log. And then we're done. There it is. We squished it down into 1 log. There we go. All right, let's do part B. Here's my 3 logs, and we want to scrunch it back down into 1. And first thing you want to do is if there's any numbers out front, you've got to put them back in their rightful place as a power on whatever the inside of that log is. So this is supposed to look like ln of x to the 4th plus ln of y minus ln of z cubed. So those become powers on your arguments there. All right, so this is where we want to start squishing our logs back together. You can do this in any order you like. I notice that I have an addition here and a subtraction. So additions were originally multiplications and subtractions were originally divisions. Again, you can do this in any order. You'll end up with where you needed to go, but I like to start with the first 2. Let's scrunch these 2 back together. Because this is an addition, this scrunches back down into a multiplication. This becomes x to the 4th times y in there. And then I'm just going to rewrite this one because we hadn't dealt with it yet. This one just gets copied down. So these 2 I squished together, and now I have 1 squished log and 1 loose log over here. ln of x to the 4th times y minus ln of z cubed. Now for this, we go, okay, now these 2 are subtracted, which means these 2 can get squished down into a division. It becomes ln of, this becomes the top, so the first log, its argument becomes the top, and then the log that's subtracted, that its argument becomes the denominator. X to the 4th y over z cubed gets squished down. 1 log with all of this inside it. And then we're done with this one. It's now compressed down into 1 log. All right, let's do this again. I think we're on a roll here. First thing you want to do is relocate any numbers and write them as powers on your variables here. So this should be ln of x to the 1/2 minus ln of y squared plus ln of z to the 6th. And again, you can do this in any order you like. Let's start with the first 2. These 2 logs are subtracted, which means when you scrunch those together, it becomes a division. A division, the first log, its stuff goes in the top. The log that's subtracted, its argument goes in the bottom. So these 2 logs squish down into this one, and since we hadn't dealt with this other log yet, we just copy it down. Now I have 1 halfway scrunched log and plus this one. So now these 2 can get squished down together, compressed. Since this was originally an addition here, that means that they get squished together as a multiplication. This times that. So then if you want to, you can write the z to the 6th in the numerator there, since that's a fraction. Be x to the 1/2 z to the 6th divided by y squared. And all of that is inside the natural log, ln. And then you're done. This is your answer. You took more than 1 log and you compressed it down into 1. All right, Let's do one more. Take these two logs and compress them together. Now this one doesn't have any powers to bring out. Now since this is something that has an expression that's added, if there was a number in front, it would have to be a power over the whole expression. So as a side note, by the way, if I had 2 ln of x plus 2, if I were to put that as a power, it has to be over the power of the whole thing. So this has to be ln of x plus 2, all of that squared. So if you have something that's a little like added or subtracted in the middle, and you have to bring a power up, it becomes a power on the whole thing that's added. So if this had a number on it, this would have had to have been a power over this entire expression. But there's no number here to bring up to make a power over the whole thing. And that's not the case for this one either. So I don't have to worry about any powers here. But I do see that I have 2 natural logs that are subtracted. So these two can get compressed together into a division. This becomes ln of, that becomes the numerator, x squared plus 7x plus 10. And then the one that's subtracted, its argument becomes the denominator, x plus 2. So we've done the compression. We've done what they asked. But then you go to plug this in your homework, and it says that it's wrong. And you're going, but I know I did it right. Well, it wants you to simplify. And that's why it's saying it's wrong. So when you have logs that you've compressed together, it's a really good idea to try to cancel anything that you can cancel, or combine like terms, or whatever you got to do to get things to work. This log, when I compress it together, all my variables are different. That's an x, that's a z, that's a y. Like nothing combines, nothing cancels. There's no like terms anywhere. This one's kind of stuck. But this one, this is 2 polynomials. I've got x squared plus 7x plus 10 divided by x plus 2. This, interestingly enough, this x squared plus 7x plus 10, that's a quadratic that can factor. So watch me do this. If I factor the top, this becomes, if you're looking for factors of 10 that add up to 7, this becomes x plus 5 times x plus 2 in the numerator. And I still have this x plus 2 from the bottom that I just copy over. So what do we notice? I notice that I have x plus 2 in the top and bottom here. That is a repeat factor, and that actually can algebraically cancel. That's allowed. So what am I left with? I'm left with ln of x plus 5. And then this is your answer. So if you have something like this in your homework, you'll want to factor and cancel anything that can cancel before you try to enter your answer. This is a plus. Yeah, x plus 5 is the only term that's left after a cancel. So factor and cancel, and then your simplified logarithm is your answer, ln of x plus 5. All right, I think that is enough for this video. Come back for the next part of this lesson, where we start using these properties to help solve algebraic equations. You know, what we would really be using all of this stuff for, solving stuff. All right, see you next time.